This is lecture 1H on sigma notation for Calculus 1. Sigma notation is a convenient way of writing sums that you can somehow index. In this example, we have the sum of the squares of the first 10 integers. You can use those integers as an index. To do that, you have to give the integer a name. We'll call it k. And then the first term is k equals 1. For the second term, k is 2. For the third term, k is 3. So I've been able to create an index out of the sum of the first 10 integers. Now that we have the index, we can use the sigma notation. So with the sigma notation, the first thing you have is the Greek capital sigma. That's right here. Okay, underneath this, sigma meaning sum. Underneath this, you write the letter, the index letter, k, and you give its minimum value. In this case, k equals 1. Then on top of the sigma, you give the maximum value for k. K will be incremented from 1 to 10 by 1s. K will go 1, 2, 3, 4, up to 10. After all this, you write the formula, the function that you're going to sum. There are a few conventions. One of them is that for the sum, or for the index or the counter, we use the lowercase middle letters of the Latin alphabet, I, J, K, L, M, and N. If you've ever programmed in Fortran, you know that these were hardwired into Fortran as integers. That reflects this convention. The sum can be written starting at any value of k. In this case, I used k equal 1, but it could start at any value, and it can go as high as infinity, or rather approach infinity, for an infinite series. To evaluate something written with sigma notation, here we are right here, say we're given this, then we start with the counter with the k, the index, at its lowest value, in this case 1. We substitute the 1 into the expression to get the first term. Here's the first term right here. 3 times 1 squared plus 4. Then increment the counter to 2. Use that to create the second term. Here's the second term. In this case, k is 2, so we have 3 times 2 squared plus 4, and that is added since this is sum, this is sigma. Okay, you increment the counter again, get the third term. Then you increment the counter again, and now you're at the 4, at its maximum value. You go ahead and let that be your last term. You evaluate the rest by arithmetic or algebra, and you get the answer. There are two interesting sums or interesting notation. You might want to memorize these because they do occur in calculus, especially with trigonometric functions. Okay, and one is 2n. I'm going to let n be any natural number. That means n is 1, 2, 3, 4, etc. Any natural number. 2n is an even number, and 2n minus 1 is an odd number. If I sum over all the even numbers, in this case, instead of using n, I'll use k as the counter. K is going to start with 1, go to infinity, and I use the 2k. Let k be 1, so that's 1 times 2. That gives me my first even number, 2. Let k be 2. 2 times 2 gives me my second even number. Let k go to 3. 3 times 2 gives me the second, and that is the sum over the even numbers. For the sum over the odd numbers, do the same setup, but then the formula is 2k minus 1. When k is 1, I have 2 times 1 minus 1, giving me the first odd number of 1. Let k be 2, I've got 4 minus 1, I get 3, and then, 3, k equal 3, you get 6 minus 1 and get the 5 for the next odd number. Again, the important thing to remember is 2n is an even number, 2n minus 1 is an odd number. There's some rules for sigma notation. One of them is that if you have a constant that does not include the index, you can still use the sigma notation. In this case, we have the counter going from 7 to 10, and the formula afterward is just a constant 5. So you do just like you did before. You let k be 7. There's no place to write 7, but I have the 5, so I write the 5. You let k go to 8. Again, there's no place to write the 8, but you have a 5, so you write that down and add it together. You keep adding until you get your sum of 20. Because k goes 7, 8, 9, 10, which is 4. There's 4 values of k that gives you 4 of the 5s, and you get the 20. There's an easier way to write to evaluate sums of constants, and that is to figure out the number of terms. To do that, you take the maximum, in this case 10, subtract the minimum, and add 1. So here we go. This would be 10 minus 7, that's the max minus the min, add 1. So we get 4 times 5 is 20. The reason we have to add 1 is because of what is called fence post problems. The idea behind a fence post problem is if you made a fence, you would have, for example, say you did it with 5 fence posts. You would have fence post 1, 2, 3, 4, 5. If you subtract 1 from 5, you get 4, which is the number of spaces between the fence posts. If you want the number of fence posts themselves, then you have to add 1 to the 5 minus 1. Okay? This problem occurs in computer science a lot, in calculation, say for fluid dynamics, or in large codes, large field solvers, where you have a certain area and you've subdivided it into the grid. If you're trying to match the boundary conditions between each of the little subdivisions, then you want the values at the edges, and you have to count all the edges. That's your fences, in other words, your fence posts. In that case, you want the fence post. If you're doing some calculation on the internal parts of each section, then you're looking at the number of spaces, between the fence posts. So if sometimes you add 1 to that difference, sometimes you don't. If you didn't add 1 when you should have, you'll miss one of the edges at the end of your grid. If you added 1 when you shouldn't have, you'll end up trying to compute something in a space way outside of the material that you had subdivided. So that's sort of the basis of the fence post problems. There are 2 more rules for sigma notation. If you have, if in the formula that's being summed you have a plus or a minus, you can break the sum at the plus and minus and create 2 different sums. For example, here's one. This one just goes from 5 to 20 over m cubed. Then you can do this other one separately. Now, if you have a constant multiplier, you can factor that out. Now, in this case, we have 2 terms connected by minus sign. I'm going to break the calculation at that minus sign, so I have 2 sums. Then the first sum would have been m equals 5 to 8 of 8 times m cubed. I can put the 8 in front. That means I can do this sum, this m cubed sum here, by itself. When I'm done with that complete sum, then I can multiply by 8. Same thing here. I can sum m squared from 5, when m is going from 5 to 20. When that sum is done, then I multiply by 5. That can really be a very great savings in the number of calculations that you have to do. But also, the fewer calculations you do, the fewer chances you have of making mistakes. The sigma notation has an analog in computing. These are do and for loops. Although do and for loops are more general than the sigma notation, it's essentially the same thing. You're going to repeat something over and over. It's going to be indexed on some kind of a counter that's running from a minimum number up to a maximum number. Now, if we look back at that idea of breaking the calculation into different pieces and factoring out common terms, if in that problem before that index went from m to 1,000, then if you did not factor out the term, you would have 2,000 multiplications. If you did factor out the term, you end up with 2 multiplications. In computing, the more operations that you have to do means the longer the code takes, the more inefficient it becomes, and the more money it costs. So to go from 2,000 multiplications down to 2 just by reformulating your problem would be a great savings.